All right, everyone. Thanks for joining us. Today we have Eric Schles, who is a data scientist from Johns Hopkins University. So a little bio about Eric. So Eric is a principal data scientist at Johns Hopkins University. He's also a PhD student at CUNY Graduate Center in New York, and he's studying machine learning and category theory. Eric will be discussing about Drifter ML. What is Drifter ML? It is a testing framework that helps ensure machine learning models satisfy the assumptions made when training the model. We'll walk through the motivations of model testing and a few examples on how to use the framework. Eric, I hand it over to you to take us away.
All right. Hi, everybody. I'm Eric. So today we're going to be talking about Drifter ML, a testing framework for testing your models after you deploy them to production. So just a little bit about me. As was mentioned in the intro, I am a PhD student and I need research collaborators so I can publish papers. So if you're interested in the topic of testing models or category theory or machine learning, please do reach out to me. These are good ways to reach me, Twitter and LinkedIn. Okay, let's talk about this. So today we're going to talk about what is Drifter ML and really like how you test models in production, why this is important, and then how to do it. So first off, let's start with what. So Drifter ML is an extensible open source framework for assessing model drift. It's written in Python 3. And it conforms to the scikit-learn API for models. So what this means is it can test any model that has a fit and predict method. So you need both of those. So you don't have to use scikit-learn. You can just literally wrap whatever framework you're using to make sure that those methods are defined. And if they are, then you can test your models with my framework. So a little bit about model drift. So the only truth of the world is that your data will change. It's going to. So your model will need to be retrained eventually. There are some rare exceptions to this. If you're dealing with closed loop systems, these are systems that, you completely control the variables. There's nothing outside of the system. It literally is just going to do the same thing within a very specified set of parameters every single time. So some of the processes in like a factory setting are more likely to be a closed loop system. Anything like that, where you have complete control of the environment that your data is coming from, in those systems, usually the models that you develop are not really going to change over time unless something changes in your closed loop system. Then you can assume that your model is going to perform the same. So basically, extant patterns are going to be extant, right? But if you're subject to exogenous variables that you can't control for, things that are outside of your control, then eventually you're going to need to retrain your model. That's just a fact. And then model drift is likely to occur because as your data changes over time, the assumptions that you use to train your model are going to break. That's just going to happen. So why test, instead of, so like the most naive thing you could do, the most naive thing to do before you even get into testing is you could just literally like retrain your models on a set schedule, like once a week or something. Now, the reason why I would say that that's a bad idea is because training models can be very expensive, right? So if you're in a production setting and let's say, I don't know, you're Google or something, and you have a machine learning model for search, right? I know they use like a bunch of those. If you're just doing this is one component of search. There's like a lot of models that go into Google search, but like let's say you're just doing one of them, right? Like the world is obviously changing at a rapid pace. If you have to retrain every single time that you're like on a regular cadence once a week, that could cost like $100,000 easy. I used to work at Pepsi, and I think we dropped like 30 or 50,000 a month on retraining models. It can be really expensive. So, and that can even be on small data. It's just about the number of models, the number of hyperparameters, what type of model you're using. All these things come into play, how much compute you need to do it. All these things matter. And so you want to retrain your models as infrequently as possible. And so if you can assess your drift, then you can train your models less frequently. And then you're in a situation where you're saving money without having to even consider compute costs or anything like that. So that's like pretty great. So we don't want to retrain unless we have to. Okay, that's the argument there. So we also want to make sure our models are doing what we expect. That's really important. So correctness and cheap training, those are the two things here. Now, obviously, if we went with the regular cadence of training a model once a week or whatever, then we would just optimize to some like labeling process, and we would meet our objective function. We would get our constraints, and then we would be fine, right? That would be okay. So it's certainly possible to meet the second criteria without a testing framework. Now, the thing is, you need labeled data in order to do that. If you do not have production labels on your production data sets, then you can't actually make sure that you're doing like that you're improving your model based on this new data that's coming out. So labeling process is typically expensive. There are ways around that, like semi-supervision or self-supervision, right? So you can have some model that like learns on some simple task, and then you can train that model, and you can generate new labels with this task that was trained on something else. That's self-supervision. Semi-supervision is you start with some small labeled examples, which is the typical case, and then you would use your machine learning process to do that labeling thing. Now, that's all fine and good, but like it still assumes that you don't have model drift. So we need a process that's going to avoid this issue with model drift and the labeling process. So anyway, all right. I digress. So in general, it's important to define what a good model is. It's something that's performant, accurate, fair and equitable with respect to specific demographic variables and other protected variables. Demography is certainly an important thing, but fairness, I think, actually has like a pretty large set of things. Anyway, and then has a minimal memory footprint. All of these things are really important. So by this is going to make your models energy efficient. It means you're not going to be spending tons of energy. So I don't care about cost personally. I mean, like there are people in like the finance department that care about how much money folks are spending on your machine learning models, but like I care about this from an environmental standpoint. So your memory footprint directly affects how much pollution you're churning into the air because of how much energy you need to generate in order to train the models, right? So if we have to spend more compute power, then we are creating more pollution, and that's bad. The environment is important. I don't think it's a controversial statement. Anyway, so the performance and the accuracy thing and this minimal memory footprint, I have tests for this in the framework. I am actually working right now on a fair and equitable testing suite. I was very hesitant for a long time, but I think I finally have an idea on how to make this fair. So how do we do this? How do we test models, right? So hopefully I provided some context as to like why retraining is important, given some counterexamples how you could do this, in other ways, but like some of these things fall short. I think, at least for a production setting. I think self-supervision and semi-supervision are great tools for when you're in a low label regime. However, when you're in a production setting, you need to turn this around fast. And like, I think semi-supervision, you can probably turn this around in like a week or something and, generate enough labels to really do something good. But like, that's a week of lag time where you're getting bad results and you might be throwing money down the drain. The self-supervision thing, I mean, honestly, I think it's really good. I think there's a lot of power in it, but it like, there are instances that I found in production when self-supervision actually falls short because of the assumptions that it makes because of the types of tasks it trains on. It's really easy to make a mistake. It's hard to do correctly. And I worry about how really ready the larger machine learning community is for self-supervision. Anyway, I should say one more thing. So that's why I think testing is the right way to deal with retraining your models in production, because most data scientists, are at least somewhat software engineers. They know how to test things. Testing is more obvious from like an intellectual standpoint. And so that's where that comes from. Okay. So what is a model? A model is a representation of your data, much like a descriptive statistic. So this, right? This process. So this actually comes out of my book, which you can find on my GitHub. But the idea here is that I'm doing MLE. So this is using MLE for the normal distribution, maximum likelihood estimation, or MLE, is the process of assuming some data and then assuming a model and then fitting that model to your data. And then what you do is you recover your fit parameters, which in this case are the central tendency and the spread, or in this case, the mean and the variance, right? So we recover these two fit parameters from our data. Now, that is a descriptive statistic. It is literally a descriptive statistic, but this is also a statistical model. We are fitting a model when we do this. Now, the model happens to learn, two parameters, in this case, descriptive statistics, but so that's the single variate case. And we can take some data, right? That's this green thing. And then we can take some simulated data, and they look pretty similar, right? Because we did a good job of fitting our data in our model, right? So we could do like, MSE or something, some standard metric, and we would probably find something similar if we didn't account for index and we just were interested in like how much coverage it was. So some like really naive metric. But this is for single distribution. This isn't like a true statistical model because there's no dependent variable. There's only an independent variable, right? But MLE, I claim, and if you don't believe me, please read my book. It's free and open source. Well, the rough draft is free and open source. There is going to be a final draft at some point that is not going to be free, but whatever. This here is linear regression. The linear regression, I claim, is just it uses maximum likelihood estimation. We assume a normal distribution when we do linear regression, right? We recover we fit some data, and then we recover a distribution. We just do it in a multivariate case. So the descriptive statistics that you've learned since, I don't know, high school are the same, is the same process, or one of the same processes you could use to recover a model. So it really makes this point, I think, clear that a model is a representation of your data, much like your descriptive statistic. It is literally a set of descriptive statistics about your data. That is what a model is in like the truest sense. It can be used for a lot more than that, and it's like a mathematical equation, description, whatever. But like really what you're doing here when you do it with the normal distribution, there's a mathematical equation there too, and you're just fitting two parameters on that mathematical distribution. I mean, the normal distribution truly has a formula. So it's the same thing. It's just this is overspecified. Not overspecified. This is correctly specified. Sorry. Anyway, so that hopefully convinces you that models and descriptive statistics really not that different. There's just a level of sophistication difference. Okay. So there's one more piece of information you need here. So, right, models are not as simple as descriptive statistics. You can't just look at a model and say, "Oh, I understand it." You have to think about it for a while. It does some stuff. So, how do we pull equivalent descriptive statistics out of a model? Well, I'm going to show you. So, this is a very simple experiment. It's trivial so that it's clear what's going on here, but it's entirely possible to make this more nuanced. Let's say that we have two situations, right? So let's say this is our training data, and then this is our production data. This is the data that happens when we put our model into production. So for those of you familiar with the Tay experiment that Microsoft did, where they put an NLP model onto Twitter, let it loose, and then let it learn from what people were sending it, and then it turned into like a murder bot within 24 hours. Say this is the training data that Microsoft fed it, and this is the production data that Twitter fed it. So these are very different distributions, right? The means are all different. The covariance structure is different. This is 1, this is 10. So these are order of magnitude different. Same number of samples, same number of features, same number of classes. All the other stuff is true. Okay. Oh, and I changed the random state too, whatever. So I just want you to really understand that these are different data sets. So I do train test split like always, create a logistic regression like always, right? Or some model, whatever. I'm choosing logistic regression. You can choose whatever you want. This experiment works with anything. And then, well, I mean, I haven't tested on every type of model, but it works with all the scikit-learn ones. Anyway, so you can do a fit, you can do a predict, and then you can get some classification metrics. Okay, that should not be surprising. None of that should be surprising. That we haven't shown you the magic yet. Anyway, so you get your precision and recall F1 score. These are all the standard classification metrics. If you don't know what classifiers are, this talk will be over your head. Anyway, so I make a pretty picture. Oh, look, we got some ROC line for class 0 and class 1. Hooray. All right. So now here's where the magic happens. So the first thing I want you to notice is that the precision and recall, F1 score, all that good stuff, right, is very different than it is here, okay? So that's the first thing I want you to just keep in the back of your head. All right, now, so I'm going to take you through the process. So the first thing you do when you're retraining in general, not specifically to this, is if you're dealing with model drift, is you have a surrogate model with the same hyperparameters as your logistic regression. So this is just assuming that your hyperparameters are correct, okay? In general, like, you would change this hyperparameters, but you would keep the general structure of your model. So like if you were using logistic regression before, right, you're going to continue to use logistic regression now. It's just you're going to change. This is going to be tuned. So I am not changing the hyperparameters on purpose. So this is a surrogate model of the same brand, but of the same kind. But like in general, you would change these hyperparameters. This is the only thing that changes when you retrain. Anyway, all right. So I've got the surrogate model, right, which just means I'm creating a new instance with the same hyperparameters. And then I'm going to create production predictions, production data predictions. So X2, as you recall, is the production model. All right, X2 is the production data. This is the trained model from the training data. So like completely different distribution, blah blah blah. We don't know that ahead of time, but we discover that by recovering these metrics. Anyway, so then I don't remember why I had to do this. There was like some reason why this like needed to happen. Don't worry about this line. But so then we have the surrogate model, okay, and we're going to fit it. We're going to fit it with X2, right? Our production data and our predicted production labels, okay? So these are the labels that we saw in production from our classifier. So like, in general, some production process is happening, and this is what we would get. This is what we would actually get. We don't. So okay. So then I look at our validation set. So the validation set comes from training data. So we still are in the training regime when we do this prediction off of our surrogate model. Okay. So we get some prediction, right? And then we generate our classification report. And as I said before in the beginning of this part, it's different. The precision and recall are different. Now, is this just a fluke that we get a different precision and recall when we're dealing with different production data, or have we actually stumbled upon something that is generalizable? Basically, have we discovered a method? I mean, obviously the answer is yes, otherwise I wouldn't be giving this talk. So have we discovered a method for assessing when a model is going to drift? Just based on the accuracy metrics that are standard for any classifier. The answer is yes, we have. And so here's another example where we have just the mean is far enough away. The covariance structure is exactly the same. The random state is still different, but like I don't know. That didn't seem to matter in these trials. Just making the mean different was enough. And so you can see here's the precision recall, blah blah blah. And here's the precision recall. And so, we can actually assess when the data has drifted just by looking at these precision recall F1 score metrics. That's pretty cool, right? That's pretty neat. And the setup's not that hard. It's just like a couple of lines. Really not that big a deal. So does this work when the data is the same? If the data is the same, do we recover similar precision recall metrics? So okay, so recall these are the 68, 45, whatever. And yeah, they're pretty close. They're not exactly the same. That's important, right? They're not exactly the same, but they're pretty close. So what this tells us is that when our data is similar, right, in the production and in the training phase, then we're good. But when it's different in production versus training, then we can assess that, and then we can say, oh, it's time to retrain. So that's like the basic insight behind this entire framework. Now, I should say that one more thing here. Notice we never actually need labels for the true labels for the production process. We only need the predicted labels for the production setting from the training classifier. So this means that we can actually assess like data drift directly from just like literally looking at these models without ever needing the true label. So we don't have to do the labeling process, which is expensive. So the reason this works is actually because of what I talked to you about already. So a model is just a description of data, right? All I'm really doing is I'm saying, like, let me take the mean. Actually, I'm going to try something that I haven't tried before. So we have some training, right? And we get like some descriptive statistics. So this is like the most naive possible model you could have, right? Maybe we have like mean T for training and like standard deviation T for training. And then we have a production setting, right? And we have mean P for prod. And all we're really doing, right, is checking like when we take the difference between mean training minus mean prod, are those less than some epsilon? And like, we can look at the standard deviation too. But that's all we're really doing here with this entire framework. And like, that is the obvious thing to do. It's just the obvious thing to do. Anyway, so that's why this works. Okay, I'm going to stop sharing my screen. Oh, that was so fun. I love this toy. I just got it, so I'm playing around. Sorry. All right. So again, the steps to use Drifter ML. Do your exploratory analysis like always. Split your training test data and validation, right? You need the validation data, otherwise this doesn't work. Use your training data, train your model, validate with your test data, store your validation data for later. We'll get to that. Oh, we already got to that, whatever. I should really take that out. Anyway, whatever. Put your model into production. Capture the data that goes into your model as well as the predicted values. Train a surrogate model with the same hyperparameters as your model currently in production on the captured data in step 7. Specifically, it should be the data your model saw and predicted, right? And because this is production, you're going to be using your predictions. So like storing those is like a reasonable matter of course. It's an artifact that you should just have. And then step 9 is you use my framework in theory. You don't have to. Test your model with Drifter ML where your ground truth is the validation data and the predictions comparing against the surrogate model. All right, so that's it. So I'm actually going to skip this slide because like I think we've already covered pretty well like why. All right. So let's look at Drifter ML. So this is the docs page. So we've got some classifier. Okay, this is just like fake data, whatever. I'm using a decision tree this time, I think. Yeah. And then you test against production with this. So this is like you can just like copy paste this into your like pipeline. Okay, so this is like yeah. Okay, so then we got this guy. Okay, I don't know where that generates twice. Anyway, whatever. All right, so now we got our tests. This is what our test.py file looks like. So the most naive thing to do is just a lower boundary for a class, right? So like when we did this, we were like, oh, okay, these are similar because like this is kind of like close to this, right? The lower boundary test is like the most naive thing you could do. We're just saying like, are all the classes above 90%? Because like in a production setting or in the training setting, they were above 90%, right? If they're not, then we assert false. That's it. That's a test. So with that, you're good. You can just like literally put this in production, right? And then you're good. Yeah. So that's it. That's like the whole shebang. It's pretty easy to write these tests. I've got like a bunch of them. That's like what's in here. So like, we'll just go to here and then into here. These are all in the documentation too, but I've got like a bunch of like documentation in the code, and like there's all of these different tests. I've written a bunch, so you can like in a really nuanced way tell like what it means for model drift to occur, right? We've got just like a bunch of these. So we've got lower boundary precision, we've got lower boundary recall, we've got ROC AUC, You can test per class. You can do like random samples and then test cross validation. Like all this stuff is possible. So I've tried to like make this framework as like feature rich as possible. Anyway, okay. So that's my talk. This is me again. Again, I'm looking for collaborators. And that's how you get in touch with me. Okay, I'm done. Yeah.
Oh, thank you so much, Eric, for that talk, for sure. I think we do have one question on the chat that I'll read out to you right now. Quaish asks, wouldn't it get really expensive to retrain the model to calculate model drift?
So no, it is not as expensive to do that because you control the size of, that's a great question. Thank you so much. It would not be expensive because you control the size of the model of the data that you're getting from production, right? So like the idea here is that you would have like a pretty minimal, like as small as you can get away with, really. Like in some cases, the answer is actually yes, right? Like it does depend. It can get expensive, but the hope is that you can train this on a minimal set of data, right, in order to assess model drift. So yeah, that's like how, because like, you know, the hope is that prediction is cheap, at least. Prediction is like typically cheap. The retraining process on the test data, on the production data is the only thing that would cost you anything. And so, you know, as long as you can find like a reasonably small sample that you're confident with, then it should not be expensive to do this. But that is a great question. It's nuanced and difficult. And assessing this, like, you know, requires quite a bit of thought. I think model drift is like a really hard problem in general, and this framework can help you assess that. But, you know, there is more that I think needs to be considered. And so I really appreciate the thoughtfulness of your question. That was like really good. Yeah.
Okay, that's good. I do have a few questions of mine, actually.
Okay, great. Go for it.
I do work on this space a lot myself. I guess one question I have is, what about PyTorch, TensorFlows, and Cafe framework? Are you planning to also explore those spaces too? Because when we think of like the I guess the models that are in production today, or some of the models that we plan to build, they have like deep learning models, they're trained on PyTorch, etc. So how does scikit-learn port over, or what you have on scikit-learn port over to a TensorFlow or a PyTorch type framework?
Oh yeah, that's a great question. Well, I mean, there are scikit-learn wrappers for the frameworks, all the frameworks you just mentioned. I don't know about Cafe, but definitely TensorFlow and PyTorch. There are scikit-learn wrappers. That's not a problem. Like that's already solved.
Okay.
100%.
Awesome.
Yeah, I think I don't know if this ever got merged in. At some point, Keras like broke like the scikit-learn wrapper. I tried to get like a PR merged, but they like closed it out. But I think they actually like fixed it. So like it should be. I think it works now. There was like a period where it didn't, but yeah, no, you can definitely just use a scikit-learn wrapper for
one more question. So how does the Drifter ML methodology you have, how does it cater to adversarial threats? So in case somebody were to dump a bunch of data and then that data just like happens to be input, or it's in production and that just causes the threat, how would your model cater to that?
I do not cover adversarial attacks at all right now with my current framework. You know, the hope would be like, so adversarial attacks in general are very nuanced, right? Like the way that you like poison your data such that like you pass something through is like in some cases very specific. Like, not to say that the adversarial machine learning space isn't really interesting. Like I think that a lot of those folks are very well meaning and they're doing like very good work. Some of their things are like just like nitpicks, but some of them are absolutely like generalizable attack surfaces. And I think being able to test those attack surfaces is really important. So the nitpicks, right? If you retrain your model, you're going to get rid of those. Those are just going to go away, right? The adversarial attacks that are like very specific to the hyperparameters that the model is trained with and everything. Those are just going to dissipate when you retrain on new data. That's just going to happen. But the generalized attack surfaces, some of the structural components of these models, are not going to dissipate in an obvious or straightforward way. And I don't have a good answer for you for my framework. I think that needs to be assessed with other tools, to be honest. Like, I mean, one of the things you could do, this is me just like thinking out loud, is you could use some of these adversarial attack surfaces that generalize to an attack surface for the structure of your model, and then include that in your testing suite. So, one of the things I say is that my model is extensible, and I truly mean that, right? You can write your own test on top of mine. And so I think it is possible to extend this to the adversarial regime with some work. It's not going to be easy, but with some work.
Got it. Yeah, good answer for sure. Yeah, so there's another question actually here from Grace, who said, if you use a smaller batch of production data, wouldn't the hyperparameters change? And this is coming from the previous question.
Yeah. So, of course, the hyperparameters would change in a sense, right? But like, it's important to correctly conceptualize what I've done. So I think it's worth it for me to share my screen again. But this is a great follow-on question. Really appreciate it. Okay, so let's go back to I need the okay. I need the thing again. I'm just going to go back to my minimal example. So okay. Yeah, this is probably good enough. All right. So notice the hyperparameters for your surrogate model are going to be the same as the one in your training data. You never need to do, okay, no, actually the hyperparameters will change. Yeah, sorry, I was a little slow to like fully internalize. The hyperparameters are going to change if your batch size changes. That's true. So how would I assess this? I think the right thing to do here is probably to make sure that your training data doesn't have too large of a batch. So this way, yeah. Okay, I think that's the answer. So the batch size that you use for your training data has to be the same batch size you use for production. But we all know that you can change your batch size, right? Like as you're training these models. And so I think that as long as your batch size is equivalent, then like you have some fixed points. Yeah, I mean, by definition, the surrogate model is not going to have exactly the same hyperparameters, and you don't want it to have the same hyperparameters as what you had for your training data. So like, I agree that you're breaking some notion of like equivalence, right? And I think that's a thing to be worried about, like a very reasonable thing to be worried about. But I think that if you use smaller data, but it still captures what ought to be the representative, sample, the representative sample for your production settings, such that you can assess model drift, right? And this is going to really come down to your business case, assessing the sample size that's of like a large enough size. But as long as you're doing that, I think you are still okay. Because, right, like it's the same thing as you would have with descriptive statistics. If we just go back to like the really naive case of descriptive statistics, right? If you're dealing with 1,000 data points and you're taking the mean of 1,000 data points, and then now we're in production and you only have 500 data points to assess off of, and you take the mean of those 500 data points, you would assume that that's enough, right? That's enough to assess equivalence between the means of your two samples, I think. So I don't know why you certainly wouldn't need it to be exactly the same. You would need it to be proportional. I think a proportionality is required though. So you are still having some expense captured here. But like, if you have to do a full retraining of your model, right? That is, I would assume, significantly more expensive than if you have to retrain, on some proportionality constant. So you save X dollars in theory, right? Like all of these things are choices. So maybe you only test the CI/CD pipeline with Drifter ML like, once a week. And so then you've saved that proportional amount that you wouldn't have to assess model drift. That's sort of like the claim here. Yeah. But these are great nuanced questions. I super like, please reach out to me. Let's connect because these are great questions.
Got it. I think there's no more questions on here. But I mean, thank you so much, Eric. I really appreciate the time you've taken. And I thank you everybody for joining us. I think that will be all for today.
Yeah, I really appreciate it. Thank you so much, everyone. This has been a great session and I really enjoyed the questions. Okay, well, have a good day, everyone. Bye.